PreAP Precalculus Notes 1.5 Determining Domain and Range of a Function. Define domain. The domain is all the values of x that have a y value. Define range. All the values of y that have an x value. Using interval notation, identify the domain and range of each graphed function below. So for the domain, it's a set of x values in which there's a y value. The graph starts from left to right after -4, and it continues and goes to the right forever. So our domain is going to go from -4 to infinity. -4 is not included because it's an open circle, and it goes to infinity. Infinity is not inclusive because it's not a number. The range, that's the y values from lowest to highest. This is starting all the way down at the bottom, that's -infinity, and it goes up until it gets to 5, and then it's an open circle. So the range is from -infinity to 5. Number 2, the domain, it starts all the way on the left, it skips over 1, then it continues to go to the right. So it's -infinity to 1, and then including 1 to infinity. We're using parentheses because we have not included infinity or -infinity, those are not numbers, and 1 is an open circle, it's not included. Range. We start at the bottom, starts at -infinity, it goes continuously up to 2. Even though it comes back down and there's an open circle at 1, there is a y value at 1, in which there's also an x value. So this range is going to go from -infinity to +infinity. Number 3, even though this is 3 different pieces to this function, the domain's all real numbers because it starts at -infinity, goes till it gets to 1, includes 1 here, and then starts after 1 going to the right forever. As far as the range goes, it goes as low as -3, not inclusive, and then this goes up forever, which includes these missing numbers in here. So it's going to go from -3, not inclusive, to infinity, not inclusive. Number 4, the domain from left to right, we're going to go from -infinity, skip over -1, and then go to 5, not inclusive. The range starts at -3, it's inclusive, it's a closed dot. It includes all y values up to 5, but then if you look more carefully, this one here includes the 5. This one actually goes down forever. So I was wrong by saying it starts here at -3. This part goes down forever. I can actually draw it. So since this goes down forever, it encompasses all of this. So our range goes from -infinity up to maybe 3.5, not inclusive. Be real careful about these arrows. So as far as the domain goes, it starts at -5, not inclusive, includes going to -1. So it looks like it goes from every place, not including -5, to the right forever. Every x value is accounted for. Range starts at -3 inclusive, and it goes up forever. Every y value is accounted for. 6, domain. This is going left and down forever. So left is -infinity. It goes until it gets to -6. I'm sorry, to -1. It is including that. So it looks like the domain goes from -infinity, hops over 2, and hops over 4. So we go -infinity to 2, -infinity to 2, hops over 2, goes from 2 to 4, hops over 4, and goes to infinity. Cool. Range goes down forever. It goes up forever. We're missing a point right here, but it picks it up right there. The range is all real numbers, -infinity to infinity. Determining domain and range of a function analytically. Constant function. Constant function is a horizontal line where y equals some number, and that number is the y-intercept. Every constant function has a domain of -infinity to infinity. A linear function is a non-horizontal line. So here's an example. The slope would be A and the y-intercept is B. Every line that is a function that's not horizontal has a domain of negative infinity to infinity, even though these both have, any function that's a line has domain negative infinity to infinity. Absolute value function, translate right B and up C, that puts the vertex here. This domain is all real numbers, negative infinity to infinity, goes left and right forever. Quadratic also has a domain of negative infinity to infinity. It is going left and right forever. Given below are the graphs of 3 different functions that we will investigate analytically. Refer to them as you complete the table below. Identify the domain of each function that is graphed. Well, this function here, which we haven't talked about to this point, this is called a rational function. The domain for this function starts at negative infinity and it skips over negative 2, and then it goes to positive 2 and skips over it. So it's everything but negative 2 and positive 2. So the domain negative infinity to negative 2 skips over negative 2, negative 2 to 2 skips over 2 to infinity. This next graph here is a square root function opening to the left. We would rather see this written as a negative x minus 5 inside the square root. That's how we're used to seeing it in this order. That's translating to the right 5. Nothing else is, well, and then it's a horizontal reflection, so it opens to the left. That's why this looks this way. This domain is going to go from negative infinity until you get to the vertex of 5. Cubed root function is this next one. Any cubed root function is going to have a domain of negative infinity to infinity. This particular one, this plus 3 inside the function translates it to the left 3, so the vertex is right here. Complete the table below as a precursor to determining the domain of each function analytically. All right, so let's check this out. We're going to take this function, which was the one that was graphed up here, and we are going to figure out what is the y value when x is negative 2. So if we plug in negative 2 in for this x value here, here, and here, you substitute, use parentheses. Negative 2 squared is 4. Negative 2 minus 6 is negative 8. Negative 2 squared is 4. 4 minus 8 is negative 4. 4 minus 4 is 0. 4 divided by 0 is undefined. Interesting. What's f of negative 1? Well, if we plug a negative 1 into this, you're going to find that we get the answer is 2. What conclusions can you make about the domain of the function based upon these two computations? Well, x equals negative 2 is not in the domain because when x equals negative 2, there is no y value. And if you look back up here, we said that negative 2 was not in the domain. What can we conclude about negative 1? X equals 1 is in the domain because when x equals negative 1, y equals 2, which is a number. Let's look at g of x, which is the square root of 5 minus x. If we put a negative 4 into this, 5 minus a negative 4 is like 5 plus 4. The square root of 9 is 3. What if we put 9 in? 5 minus 9 is negative 4. The square root of negative 4 is undefined. It's 2i. We do not use imaginary numbers in here, so this is undefined. What conclusions can we draw about these computations? When x is negative 4, x equals negative 4 is in the domain because when x is negative 4, y is 3. X equals 9 is not in the domain because when x equals 9, there is no y value. If you look back here, we said the domain for this function was negative infinity to 5. Keep in mind this is the same here as g of x. So we put 9 in. 9's not in the domain. We got something that was undefined. Not a coincidence. What about h of x? If we put negative 11 in, negative 11 plus 3 is negative 8. Cubed root of negative 8 is negative 2. So we would expect negative 11 to be in the domain. That's our conclusion. Put 5 in. 5 plus 3 is 8. Cubed root of 8 is 2. We would expect that to be in the domain as well. X equals negative 11 and x equals 5 are in the domain because when x equals negative 11, y equals negative 2, and when x equals 5, y equals 2. Rational functions. Rational function is when you have variables in your denominator. Based on your observation of f of x in the table on, it says page 46, but I think it's on page 23. Not the right page number. What conclusions can you make about about how to determine the domain of a rational function? The domain of a rational function is all real numbers, except for any x values that make the denominator equal to 0. So assume the domain's all real numbers, except any numbers you could put in the domain that make it equal to 0. Let's look at an example. Let's say the directions for this, which aren't here, which should be here, find the domain of this function. So what we do is we state the domain cannot be 0. You factor the domain. This is already factored for us. Set each factor and say each factor can't be equal to 0. X minus 3 can't be 0. X minus 1 can't be 0. Solving each of those, we get x can't be 3 and x can't be 1. So the domain is everything but 1 and 3. So we go negative infinity to 1, skip over 1, 1 to 3, skip over 3, 3 to infinity. This is everything but 1 and 3. Number 2. This one's more complicated because the denominator is not factored. If you factor the denominator, you're going to get the difference of two squares. It's an x minus 3 and an x plus 3. We set our denominator, and we say it can't be equal to 0 because that's when the function's undefined, so those numbers can't be in the domain. So x minus 3 can't be 0, x plus 3 can't be 0. We get x can't be 3 and x can't be negative 3. So the domain for this is all real numbers except for 3 and negative 3. So that means we're going to go from negative infinity to negative 3, skip over negative 3, negative 3 to 3, skip over 3, and 3 to infinity. This next problem, isn't factored once again. The top factors into an x minus 2 and an x plus 1, which is not really important right now, factoring the numerator. The denominator factors into a 2x plus 1 and an x minus 3. If you don't remember how to factor, there are some places on my website that remind you how to factor. If you need help finding those places, let me know and I will help you with that. We set the denominator, say it can't be equal to 0. So 2x plus 1 can't be 0 and x minus 3 can't be 0. If you solve the first equation, you're going to get x can't be negative 1/2, and the second one, x can't be 3. So the domain, assume it's all real numbers except for these exclusions. So it's going to go from negative infinity to negative 1/2, skip over negative 1/2, to 3, skip over 3, and go to infinity. Square root functions. Based on your observations of g of x on the previous page, what conclusions can you make on how to determine the domain of a square root function? First of all, here's a term. Whatever's inside a radical is called the radicand. The domain of a square root function will be the interval of x values that make the radicand greater than or equal to 0. See, if you have a negative If you're square rooting a negative number, it becomes imaginary, the answer, which we would say is undefined then. So we want to make sure that our radicand is either positive or 0. We do not want it to be negative. So in example F, we want to find the domain for this. We are going to take the radicand and say that has to be greater than or equal to 0. So x plus 3 is at least 0, which makes x greater than or equal to negative 3. Therefore, the domain goes from negative 3 to infinity. It includes a negative 3 and goes to the right forever. Number 2, make sure our radicand is greater than or equal to 0. Our radicand is 4 minus 2x. We subtract 4 from both sides, and then this next part is pretty important. If you're solving an inequality, which we are, if you multiply or divide both sides by a negative number, your inequality sign changes direction. So this becomes x is less than or equal to 2, where it was greater than or equal to originally. So the domain for this is everything to the left of 2, which means negative infinity to 2. Last one, h of x. We want to say that our radicand has to be at least 0. We're going to set the radicand greater than or equal to 0. We're going to subtract 1. We're going to divide by 3. So our domain goes from negative 1/3 to infinity. It includes the negative 1/3 because of the equal sign. Cubed root function. Based on your observation of h of x on page 24. I think it was page 24. Yeah, 24. What conclusions can you make to determine the domain of a cubed root function? Well, cubed root function has a domain that's negative infinity to infinity. Unless there's a radicand, if the radicand is rational, in other words, if it's in the bottom of a fraction, then some exceptions can fall from this. So number 1, this is a cubed root function. So the domain, we know automatically, negative infinity to infinity. Number 2, it's cubed root. Its domain's negative infinity to infinity. Now number 3 is misleading. You look at 3 and you think, well, that's a cubed root function. It isn't. This is a rational function because there is a fraction in it in which the variable is on the bottom. So the domain for this is not all real numbers. We have to make sure our denominator doesn't equal 0. So we are going to say that our denominator can't be equal to 0, solve for x, and we get x can't be negative 1/2. So our domain goes from negative infinity to negative 1/2, and then from negative 1/2 to infinity. That concludes these notes. Please do homework section 1.5.